Alright, hello everyone. This is going to be a Chapter 6 review. I'm just going to add to the OpenStax playlist some more videos. So these are Chapter 6 problems. So we're just going to do a couple of these. I kind of just picked randomly from the recommended list. There's like 5 questions here. So we're just going to start from the top. Problem 39. A student's backpack full of textbooks is hung from a spring scale attached to the ceiling of an elevator. What is the elevator's when the elevator is accelerating downward at 3.8 meters per second, the scale reads 60 newtons. So part A, what is the mass of the backpack? So we know that in chapter 6, if we go to our formula sheet, we see that the sum of the forces equals ma. And a little tip for doing these problems is if it's asking you, so for part A, it's asking you for the mass of the backpack, you want to try to remember any formula that has mass in it, so just the mass variable. And since this is chapter 6, it's kind of a giveaway, but on the exam you won't know that, but you will know that it's asking for mass, or m. So, and it's talking about forces, so we know that this is probably going to involve this formula, so let's write that down. So the sum of the forces equals mass times acceleration. And we know that acceleration, we have two accelerations in this case, right? Because we have gravity equals negative 9.81. And then we have this downward acceleration in the elevator, which is kind of like a reference frame. So let's just call it LE. I mean, that's silly. Let's just call it A sub E equals negative, should be negative 3.8, but because it's downward, right? Alright, so we have a gravity, we have our accelerations of these two components for acceleration, and then we have the scale, which is inside the elevator. So the force, the scale on the scale. And we'll just call this F sub B for backpack. This is 60 newtons. So this is all the information we have. We know that we're probably going to have F equals ma equation formula. We know that gravity is relevant, like with most problems, if not all problems on the exam. And then we have this acceleration downward in the elevator, and then we have the weight force, I guess, you can think about it like that, as the of the backpack in the elevator. So now I'm just going to draw a little picture to help you visualize what's actually going on. So I don't know how exactly it works, but in this elevator, there's a backpack, and I'm not very good at drawing backpacks, but oh gosh, that's terrible. Just imagine a backpack in the elevator. Something like that. Oh my gosh. Maybe there's extra storage or something. Anyway. And then you can see the force on the scale. It's reading out somehow. 60 newtons. Alright, and we know that it's accelerating, the whole elevator is accelerating downward at 3.8 meters per second squared. So under normal conditions, we know that the force of the backpack would just equal g gravity times m. But we know that's not exactly the case here because it's accelerating downward as well. So we need to combine both these accelerations into this formula. And you want to think about it logically. If the scale is reading how much force downward the backpack is putting on it, we have to realize that the backpack is going to be putting less force on the scale because of the because the scale itself is accelerating towards the backpack, if that makes sense. And the scale is reading how much it's extending. The backpack is pulling away from it. So logically, it makes sense that we should subtract the magnitude of gravity by the magnitude of this one. I really wish I could say that better, but I mean, it makes sense, right? Like if you are in a roller coaster and it goes down, you're not going to feel like you're in your seat. You're going to feel like you're being pushed upward a bit. That's the same idea here. So, all right, let's just apply that idea to this formula. So we know the formula. We know it's F equal ma. Sorry, we know the force, which is 60 newtons, and we know that we were trying to find mass. So we need to combine these two accelerations. So negative 9.81 minus negative 3.8. So minus and minus is a positive. 0.8 meters per second. I don't need to write the units yet, but you can see that we're going to have to divide. I really wish I could explain this better. It's kind of annoying. Surely that makes sense though. Like for example, if the backpack was just stationary, it was just a static object that it couldn't move, and then the whole entire this whole entire system was just moving downwards, you can see how that would compress the spring, right? Meaning the force would go down because it's actually measuring how much the spring is stretching. So hopefully that makes sense. That's why it's going to decrease the amount. So let's just find out what the acceleration is. So negative 9.81 plus 3.8, that is around negative 6.01. And then we just divide both sides by roughly 6. So 60 newtons divided by negative 6.01 newtons. And this should be meters per second squared, not newtons, what am I saying? And we're going to get a negative answer, but this is mass, so you instantly take the absolute value of that, no matter what. Maybe I used the units wrong, or sorry, I did the wrong sign or whatever, but it really doesn't matter as long as you have the right sign in the end. So mass equals 9.98. I mean, the answer says 10 kilograms, so I'm just going to write 10. M equals 10 kilograms. So that's part A done. So let's go ahead and do the other parts, and then I'll probably end the video here, and I'll just do a separate video for each, just because I hate running into mistakes and trying to figure out what to do. And then the video becomes 30 minutes long. Alright, so part B, and I fixed my pen, which is nice. Anyway, what does the scale read if the elevator moves upward while speeding up at a rate of 3.8 meters per second squared? So, as you can see, this is going to increase the amount the scale is going to read, right? Because this whole thing is now moving upwards, meaning the backpack is going to have more force acting on it in the downward direction. It's such a hard thing to explain, but hopefully it makes sense. So now the spring is like really stretched. It looks all distorted and stuff. Then your backpack is right here. It's like, whoa, slow down. But the elevator doesn't care. It's worried about going upward at 3.8 meters per second squared. And then we have an unknown force on the scale, and it's asking us to calculate that, right? Yep. So we now know the constant mass from part A. So that's another thing we know, along with all this stuff. Except this acceleration is now positive. So let's go ahead and put that over here. And we just make this positive with a single little line added to it. And we move this mass up as well. Just going to copy that. So this is everything we know. This is a little diagram. Let me zoom out a bit. Whoops. Okay. So again, we're just applying F equals ma. Chapter 6 is probably the easiest chapter, I would say. Either chapter 6 or chapter 5. Probably chapter 5. Because there's these inclines that really confuse me sometimes. Okay, so F equals ma, or B. What is the scale read if it's upward? Alright, so this time we know that the force is going to be greater. We just kind of have to use your intuition, right? Like, you're stretching on the scale more, the force is probably going to be greater than 60. So that means in order to have a greater force, we need to have a greater acceleration. So that means we want to increase this magnitude as much as possible. And that's how I approach it, at least. It's probably not the healthiest way to approach it, but um, it makes sense. So negative 9.81. So what sign are we going to use to increase the magnitude? Well, if this is positive, we want to subtract. So subtract 3.8 meters per second. We don't need the units. I did that last time as well. Okay. So now the magnitude is going to be greater. The absolute value, or whatever. 9.81, 3.8. So this is like 13.61 meters per second squared. Why did I do that? So F divided by 13, or sorry, what am I doing? We're finding F, so then we just plug in the mass that we know, and it's 10 kilograms. So we can do this in our head. 10 kilograms, 10 times that number. So F equals 136.1 newtons. And what is the answer? Oh, what did I do wrong? I mean, it's close enough, right? It's gotta be. Apparently this should be like 140. But I think that might be an OpenStax textbook problem. Yeah, we're just gonna go with that. Like, I don't know exactly how else you would approach this problem. This seems to make the most sense. We can recalculate it. Yep, I still get the same answer, 13.6, so we're just going to stick with it. Let's move on to part C. What does the scale read if the elevator moves upward at a constant velocity? If the elevator has no brakes, oh sorry, that's part D. So yeah, constant velocity, that means there's no other external force besides gravity and mass. Sorry, gravity. So if the velocity is constant, there's no other force acting on it, so it's just the weight force, right? If you have a scale, there's no other acceleration. I need to stop drawing backpacks. They're just getting worse and worse. Right, so if you have no other force acting on this besides gravity, and that's what it's saying, if the velocity is constant, that means their acceleration equals 0. So that means if you were to do F equals ma, this would be 0, and then that means the force would be 0. So there's no other force acting on it besides gravity. So that means all it is your mass times gravity, and that'll equal the force. So our mass is found, it's known to be 10, and then we all know gravity is 9.81. So your force is negative 98.1 newtons. And we see that that is our answer for part C. Okay, let's move on to part D. Part D says, if the elevator has no brakes and the cable supporting it were to break loose so that the elevator could fall freely, what would the scale read? Oh, this one's interesting. Seems to me like the scale would probably read 0. So this is just intuition, right? With every problem, you want to try to think about it intuitively before you even approach it, so that you know what the answer should be. So if a scale is holding a backpack and then that elevator, yeah, that says what the solution is, but let's try and figure out why. So with the other one, the 3.8, we tried to subtract that, and that was, sorry, not that one, this one, when the acceleration is going downward by 3.8, we knew that the force would take away from that gravity acceleration because it's kind of acting, um, the scale is reading what the force is downward, but you're also moving downward. The scale is moving downward, so that means it's going to read a smaller force. So we can apply that same logic here. It's saying the scale is moving down at 9.81 meters per second instead of 3.8. So that means the acceleration is actually going to be 0, right? So again, let's draw a diagram. There's going to be no tension in this spring because whatever gravitational force the backpack has on that spring, it doesn't register because the elevator is falling with the backpack. Now that makes a bit more sense to me, at least. Right? If you're trying to measure something, if you're trying to measure the weight of something, and like you're both falling as you're on the scale, I mean, it's not going to work. You can't even do that. So same thing here, I think. So negative 9.81. It's definitely not double the acceleration because that would not make much sense. Alright, so force equals ma, same deal. But now we have negative 9.81 minus a negative 9.81. So that's plus, and that equals 0, and it cancels. So that means force will equal 0. And we see in the solution that that is indeed the answer. So hopefully this conceptually makes sense. If it doesn't, please ask questions. Maybe someone will leave a better explanation, or I'll look it up and try to explain it better or something. But yeah, if you enjoyed this little video on chapter 6, question 39, then please leave a like, and yeah, that's it. Thanks for watching.